Hi everyone, welcome to the lecture 7 in this course Classical Mechanics 1. So in the last week we have studied introduction and then Newtonian mechanics and then degrees of freedom, generalized coordinate, constraints and basic introduction to all these subjects. So and we have learned few important concepts which I mentioned. I'll recap a little bit, but before that let me write the title of this lecture. So lecture 7, and this week we'll spend on this virtual work, D'Alembert's principle, simple, and equation of motion. So recap of last week. So in last week we have developed key concept. Now in this week we'll see that how a classical system can be described through some equations. So the key concept in the last week. So we have learned, so now I'll go reverse order. So we have learned generalized coordinate, because we need generalized coordinate, because if you have a constraint in the system, then all variables are not independent. So we need to find the independent variables, and independent variables or coordinates are the generalized coordinates. This is required. So we have discussed the generalized coordinate and analyze with examples various system with how many generalized coordinates are required. Second important, generalized coordinate is also associated with the configuration space. So this concept also, configuration space is important because every point in the configuration space represents the system, classical system. So when we consider the time evolution of the system, it is basically how the system travel from one point in the configuration space to another point in the configuration space. Second, that we have learned in details the constraints. And I mentioned that constraints impose two problems in the study. Classical mechanics, the study of classical mechanics. So I already mentioned what are these problems. Problem one is that problem we face because that all variables are not independent because of the presence of constant. So this is the problem. So one has to be careful to which variable is dependent, which is not independent, and what are the and second problem, this the first problem can be for holonomic system. For holonomic system, this problem can be addressed this problem can be addressed with the concept of generalized coordinate. Now second problem is the more serious problem, and that is the topic of studying. That second problem is that if we don't know the force of constraint a priori, so when the force of constraint are not known a priori. So if we don't know the course of constant, then how will tackle those? So this is the very serious problem. So this problem is a serious problem, and we need to develop some theory, some technique, some trick to address this problem. And that is the problem, and that is the thing that D'Alembert's principle and virtual work. So this problem can be handled by the concept of virtual work and D'Alembert's principle. So today's class is that mostly will focus on that, what is virtual work, what is the virtual displacement, all these concepts. And these are little bit conceptually, so maybe we'll teach today, and then we'll repeat again, and also we'll discuss this in tutorial class. So let me define virtual displacement and then explain. So the definition of virtual displacement. So virtual displacement, let me write change in the configuration space configuration of the system, that is configuration of the system as a result of any arbitrary infinitesimal change change of the coordinates delta I. So this displacement, and this has to be consistent with the forces and constraints impose on the system at a given instant of time. So the important point is that a given instant of time. Okay, and another important thing is that consistent with the forces and the constraints imposed on the system. So let me repeat the definition. So change in the configuration of the system as a result of arbitrary infinitesimal change in the coordinates delta Ri, which is consistent with the forces and the constraint imposed on the system, and a given instant of time, no time is taken, this is most important, no time is taken to happen this displacement. So what is the difference between the virtual displacement and the real displacement? So let me write the real displacement. Real displacement occurs in a time interval. So real displacement occurs in a time interval, whatever small, but it has always occurred in a time interval. But during that interval, so during the interval, the forces and constraints can be changed. That means force can change with time, it can evolve with time. So the real displacement occurs in a time interval. It takes some time interval, and whenever it interval, during that time interval, the force can evolve, the constraint can change, and that makes the difficulties. So by virtual, which is not real, we consider that this displacement occurs in no time, instantaneously. So virtual displacement occurs with no time, it happens instantaneously. So this is the difference with the real. And main idea is that, so there is no time to the constant force or the force in the system to evolve in case of virtual displacement, because we don't know the forces a priori. Beforehand, we don't know the forces. So what we assume that there is a virtual displacement, and this virtual displacement is taking no time, so we don't have to consider that how the forces evolve during this time interval. And that will help us to obtain some equation of motion that we are going to, through D'Alembert's principle, that we are going to discuss now. So now let us consider a system in the equilibrium. In the equilibrium, okay, for a static case, so for static equilibrium, so for a static case, applied force has to be 0. Total force on the ith particle, so suppose there are many particles, total force on the ith particle will be 0, and for I equal to 1, 2, 3, 4. And virtual work done by this force, then we can write the, so whenever we work done due to the virtual displacement, we call the virtual work done. So virtual work done by this static force on the ith particle is given by Fi dot del I equal to 0, because all the Fi are 0. So whenever you sum, so this is straightforward, right? So now let us denote this as equation 1. We are going to do a long derivation, so it will be better to name the equation. So let us consider this is equation 1. This applied force, this force on the ith particle, this can be applied force, external applied force, or it can have a, it can be a constant force. So let us denoted applied force with Fa, and the force of constant on the ith particle this. So this force can be applied force or the force of constant. Okay, so this we denoted by, say, equation 2. And if we substitute equation 1 in equation 2, so equation 1 now implies that sum over I F I applied plus Fi dotted with the virtual displacement. So all are vectors, so we should not forget putting vector sign, will be equal to 0. Now this is the main thing. If we consider, so if we consider the system system in such a way that net virtual work done work done is 0. Virtual work done by the force of constant. You can ask that where this kind of condition holds, but this kind of condition, so we are considering this condition. Now we can ask that where this condition holds. This condition holds for rigid body, so this condition body and many other systems. So this will put as a condition that virtual work done by the all force of constraints equal to 0. So in that situation, this equation, so let me write this as equation 3. So in that case, the equation 3 will be reduced on this condition as sum over I f I now applied dot dri will be equal to 0, and for static equilibrium. Static equilibrium, and this we denote by equation 4. So here I want to point out, I want to give an example that how the work done by force of constant 0. So before that, this is the principle of virtual work. So this is principle of virtual work, and for the static system, for static equilibrium, we will later consider the dynamical system. But before that, just give an example such that you can realize that how the virtual work done by force of constant can be 0. Suppose a particle moves on a surface of a sphere. So if you have a surface of a sphere and the particle moves this. Now the force of constant is the reaction force, and it is perpendicular at each point. It will be the perpendicular. So force of constant to the surface, and the particle moves tangential to the surface. Okay, so particle moves tangential, this is particle motion, and this is the perpendicular direction. So the force and the displacement are perpendicular each other, implies the work done is 0. Okay, so this is an example of that how virtual work done by the force of constant can be 0, and there will be many more example. Now I come back to the principle of virtual work. So at equation 4 we have the principle of virtual work. Equation 4, that principle it says, it implies that all coordinates are not independent. All coordinates are not independent. How? So let us consider there are only three coordinates. So it is fi applied dot delta ri sum over I. Let us consider there are three particles. So it will be f1 delta r1 plus f2 delta r2 plus uh, f3 delta r3 equal to 0. So this implies, so this implies that all r1, r2 and r3 are not independent. They are related because f1 not equal to 0, not equal to f2, not equal to f3. Okay, so this is we arrived at the principle of virtual work for the static equilibrium system. Now what happens if the system has a dynamical situation? So principle of virtual work for the dynamical situation. Okay, so for dynamical situation, your Fi is basically the rate of change of momentum, so Pi dot. Okay, so we can think of that Fi minus Pi dot, this as the force in case of static equilibrium. So static particle at equilibrium, so we can consider the dynamical situation as a static situation under the force, under the force Fi minus Pi dot equal to 0, right? That is earlier case when there is no dynamics, there is no Pi dot. Okay. Okay, so now this at equilibrium, I just follow the procedure in case of statistical case, sorry, static case. So let us denote this as equation 5, and then the principle of virtual work at equilibrium, then equilibrium, this will be sum over I Fi minus Pi dot delta del I will be 0. So this is my equation 6. Again we can write the force Fi as Fi applied plus the constant force on the ith particle. So we can substitute this. So this again, let us write, this is equation 7. So putting equation 7 in 6, we obtain Fia plus Fi dotted with delta Ri equal to 0. And then if you consider the principle of virtual work, work. What is that principle? That work done by the all force of constant will be 0. So principle of virtual work, that Fi dot del I, that will consider as 0. This is the principle of virtual work. So we'll have D'Alembert's principle. So this principle is D'Alembert principle will be sum over all particle Fia applied force dot with delta Ri will be equal to 0. So after applying the principle of virtual work, we obtain for a dynamical situation, and let us denote this equation by equation 9. Okay, so I'll probably stop here today, and we'll continue with this D'Alembert's principle. So we come to know the D'Alembert's principle, and we'll continue. So these notes are important. That equation number will refer to this equation in my next lecture. So please remember this equation, and from here we'll consider how one can obtain the equation of motion, and that will be the topic of next class. So in lecture 8, we'll derive that equation of motion from D'Alembert's principle. Okay, so far today, thank you.